Have you ever just stopped and wondered how things, well, how they move? It's kind of wild to think about, but everything from a leaf drifting on the wind to a rocket blasting off has a single secret rule behind it. Today, we're going to pull back the curtain on that rule, the one that governs every single push and pull in the universe.
Okay, let's dive right into this. Think about it for a second. Why can you send a little toy car flying across the room with just a flick of your finger? But if you try to push a real car, it feels like you're trying to move a mountain. I mean, they're both cars, right? Well, that little everyday mystery is exactly what we're going to solve. So, the answer to our car puzzle isn't some kind of magic. It's all about physics. And to crack this case, we need to introduce our three main characters, our three key clues in this whole story of motion: force, mass, and acceleration.
First up, we've got force. Now, this one's probably the most straightforward of the bunch. It's exactly what it sounds like. It's any kind of push or pull you exert on an object. It's the action, the effort you're putting in.
So, when you're straining with all your might against that real car, you're applying a force. And when you just gently flick that toy car, yep, that's a force too. It's all about the oomph you put behind it, whether it's a huge shove or a tiny nudge. All right, our second clue is mass. And you're going to want to pay attention here because this one is a really big deal. Mass is just the fancy science word for how much stuff, how many atoms are packed into something.
A really great way to think about mass is to just think of it as an object's stubbornness. Seriously. The real car, it has a ton of mass, which means it's incredibly stubborn. It does not want to move. The little toy car, on the other hand, has almost no mass, so it's not stubborn at all.
And that brings us to our final clue, acceleration. Now, this is the result we're looking for, right? It's the change in motion. And here's a key thing. It's not just about speeding up. Speeding up, slowing down, or even just turning a corner, any change in velocity is acceleration.
See, that's our goal here. We're trying to cause an acceleration. We want to change the car's state from just sitting there to actually moving. The whole challenge isn't about getting it to a certain speed, it's just about getting it to change its motion in the first place.
All right, quick recap. We have our three clues: the push we make, which is force, the object's stubbornness, which is mass, and the change in motion we want, which is acceleration. So how do all these pieces fit together? Let's uncover the secret rule. It actually works in a way that makes a lot of sense. Imagine you've got a bowling ball. If you give it a stronger push, a bigger force, it's going to speed up faster, right? You're going to get more acceleration. The logic is just super simple. More push equals more change.
And what's so cool is that this reveals this incredibly simple, really elegant relationship between our three clues. It's a relationship so perfect it can be captured in a single, powerful little equation. And there it is, the big reveal. Newton's second law of motion. Force equals mass times acceleration. F equals ma. This is it. This is the secret rule, the solution to our car mystery, and honestly, one of the most important equations in all of science.
And please, don't let those letters fool you into thinking it's just some boring math problem. This is a huge statement about how the entire physical universe is bolted together. It controls everything from how a planet orbits the sun to the way a tennis ball bounces. Okay, so we have the rule. Now let's take it out for a spin. Let's see how this one simple idea plays out all around us in things that are ridiculously huge and things that are unbelievably fast. And right here, this is the answer to our puzzle. Look. On the left, you've got a massive force, like a baseball bat, hitting a tiny little mass, the ball. The result? Insane acceleration. The ball just lunches. But on the right, well, that's us pushing the real car. Even if we use a big force, the mass is just so gigantic that the acceleration we get is almost zero. Puzzle solved. And what's truly mind-blowing is that this law isn't just descriptive, it's predictive. Engineers use F equals ma to calculate the exact force needed to get a rocket into orbit. Car designers use it to build crumple zones that literally save lives in a crash. It's how we figure out how to land a rover on Mars and how to build skyscrapers that won't fall down in an earthquake. It is absolutely everywhere. So, the most important thing to take away from all this is that F equals ma isn't just a formula you memorize for a test. It's like a powerful new lens for seeing and understanding the world around you. And now you have that lens. The next time you see a leaf fall, or you watch a car brake suddenly, or see someone kick a soccer ball, you won't just see the action. You'll see the invisible dance between force, mass, and acceleration that's making it all happen.
So I'll just leave you with this one thought. You get the rule now. You know the secret. When you walk out the door today, what pushes and pulls are you going to notice that you maybe never saw before? What are you going to see move differently?